on the first slide that I show you, you don't have to write anything down because it's the principle of mathematical induction that you wrote down at the, during class yesterday. So I just want to kind of review what are the steps to the mathematical induction, and then we'll also take those steps and kind of put them in our own words. What you need to be thinking about when you're going through your proof, have I done these things? So the principle for mathematical induction that we looked at yesterday says that we have to have some statement involving positive integers. And we're going to be doing proofs with sequences and series. So our proofs are really going to be proofs for the sum of a series. We'll be proving different formulas. And P sub n, we're going to change today. We're not going to use the P today. We're going to call it S sub n because we're talking about series, sums. And then reminder that yesterday you wrote this down. We want to do two things. We want to prove P sub 1 is true, and then we want to show that the truth of P sub k will imply the truth of P sub k plus 1, meaning 1 implies the next, and there's our domino effect, so that if I can prove 1 and that they prove the next one, then I've proved everything. And so that was a big question for us yesterday when you were thinking about, like, how do you know when you've proven something? In a real proof, in a real mathematical proof, we would know we've proven something when we have proven it for all cases, without a doubt. So proof by induction is one way to prove for all cases. You prove the first case, you prove one case implies the next case, and you have it all done. So in our own words, and you might want to jot this down today, the principle of mathematical induction, what it actually means to us is we're going to be looking to do two things. Number one, we want to verify a formula for n equals 1. So this is us proving the S sub 1, or P sub 1 in the principle of mathematical induction. Step 1 is a very easy step. You'll be provided with the formula that you're trying to prove. So all you're doing is substituting 1 into that formula and showing that it is your first term. Step 2 is the piece that gets a little bit more challenging. And this is where we introduce our k plus 1. We're going to make an assumption after we prove it for the first, that it is true for some n equals k, any integer. And then we're going to, after that assumption that it is true for n equals k, we're going to prove that if it were true for n equals k, that it would be true for all k plus 1. Now, that piece where we're using S sub k plus A sub k plus 1, you'll see that in our first proof. I'll kind of label that for you. This is where we're getting that. But each proof by mathematical induction kind of works the same way. So we kind of have the same chunk. And then at the very end, if you can get it to be the same, which you should, all the things that I asked you to prove today should work out, then you just make a statement, then the statement is true for all positive integers. You've proven it in all cases because you've proven it for the first, and you've proven that 1 implies the next. Everything is done. Okay, so here's our first formula that we're going to prove. We're going to prove that 1 plus 3 plus 5 plus 7, so on and so on, is equal to n squared for all n's greater than or equal to 1. We have to make like a general statement. So I'm going to make a statement where, like in the general or in the principle for mathematical induction, it says we have some p sub n. I'm going to make it s sub n. So I'm going to say this. Let s sub n equal the thing I'm trying to prove. 1 plus 3 plus 5 plus 7 for all odd numbers, and it equals n squared. So that's the general statement that I'm working with. I'm going to attempt to prove this by the process of mathematical induction, which requires me to do two things. So remember, the first thing I need to do is prove that that formula, n squared, is true for the sum of the first term. So step one, I need to prove this works for s sub 1. The formula is n squared. I'm going to put 1 in for n. So the formula tells me 1 squared is equal to 1. And if I look back in my series, if I add only the first term in the sequence, the sum is 1. So is that true? Yeah, I proved it. Some people like to write after this, like they might make a statement and say something like s sub 1 equals 1 squared equals 1, which is true. You could write that if you wanted to, but by putting it out there, we can make the connection that that is in fact true to the very first term. Now, the second part of mathematical induction is we want to prove that s sub k implies the truth of s sub k plus 1. So we're going to make an assumption. Assume s sub k equals 1 plus 3 plus 5 plus 7, all of the odd numbers for whatever value of k I might be. So I'm just copying my previous work, replacing n's with k's. But let's assume, for whatever this value of k is, that it is in fact k squared. So we're making an assumption. The sum of k terms is k squared. We need to show that s sub k plus 1 would be equal to, and we're going to go into this formula and we're going to plug in the k plus 1 like we did yesterday. So we want to prove that s sub k plus 1 is equal to k plus 1 squared. Okay, this is our objective. If you think back to geometry, it's like when your geometry teacher gave you some givens. These two angles are congruent, these two sides are congruent, and then gave you a proof statement. Prove that this triangle is congruent to this triangle. So here we're saying, we're assuming this to be true, so that's kind of like our given. And now we want to get to, through algebra, s sub k plus 1 is equal to k plus 1 squared. So I always write that sentence almost exactly like that. I say, assume this, show that, and I do my k plus 1 term. And then right below that, we're going to do algebra. So right below that is where we show our work for s sub k plus 1. Now this is asking me to do a sum, correct? of k plus 1 terms. So I'm going to go up to my assume statement, and again, I'm going to kind of copy the same thing I had before. 1 plus 3 plus 5 plus 7, all the way up to 2k minus 1. But that would just be s sub k, and I really want to add an extra term to it, don't I? So that I can prove the truth of the next term. So I have to add the next term, where I would do, and I'm going to do a little bit of work up here, 2 times k plus 1 minus 1, which if I distribute, that's 2k plus 2 minus 1, or 2k plus 1. So I'm using the rule, not the formula here, to plug in for k plus 1. And this is just me showing a little bit of algebra work, how I got 2k plus 1 as the next term. Okay, let's break up this line and see what we have right here. From 1 plus 3 plus 5 plus 7 all the way to 2k minus 1. That matches what we have up here in our assumed statement, correct? So this is my s sub k. Okay, all of that is s sub k. And then this piece right over here is my a sub k plus 1. It's my extra term because I have to add the next term up. Okay. And I got the a sub k plus 1 term from this a sub k rule up here. I plugged in k plus 1 for k. And then I distributed, and then I combined my like terms. Okay, so on the next line, we're doing algebra, remember? I'm going to use substitution. I assumed that s sub k was equal to what?
K squared.
Just k squared. So where all of this stuff is in red with s sub k, I could just write k squared. And I'm going to add to it the other term, the extra term, the k plus 1 term. So plus 2k plus 1. That's a trinomial. Can you factor k squared plus 2k plus 1? Yeah, factors of 1 that add to make 2 are 1 and 1. So that's k plus 1 times k plus 1, which we could write as k plus 1 squared. And that's what I wanted to show. I wanted to prove that if this formula was in fact true for k squared, that it was true for k plus 1 squared. So this statement matches this statement right here. I just completed my proof. So I'll make one final statement where I say something like, thus the statement is true for all positive integers. always start my proof with like a statement. Let S sub n equal. Okay, where I kind of write the problem. So that's how I usually start out my proof. Let S sub n equal 2 plus 7 plus 12 plus 17 plus 5n minus 3 and that's supposed to equal n over 2 times the quantity 5n minus 1. Step 1, prove it for S sub 1. So every time you start with S sub 1. So step 1, prove for S sub 1. Which means you're going to the formula and you're plugging 1 in for n. So we're going to say 1 over 2 times 5 times 1 minus 1 5 minus 1 is 4, so that's 1/2 times 4, and 1/2 times 4 is 2. And you'll notice that 2 matches if you were just to add the very first term with itself, or just keep the first term by itself, I guess. So that is proven. Got one piece done. Now we need to prove that second piece, that any k term implies the k plus 1 term. And so we'll make that very first statement, the assume and what we want to show. So we know where to start our proof and where our proof is supposed to go. So we're going to say for step 2, assume S sub k is equal to 2 plus 7 plus 12 plus 17 plus 5n minus 3. Oh, got to change it to a k. 5k plus minus 3 is equal to k over 2 times 5k minus 1. So in step 2, you always start by just replacing the n with k. And we want to show that S sub k plus 1 is equal to, and we want to go to that formula that we're trying to prove at the very end of our S sub k statement, and we want to change all of our k's to k plus 1s. So that work that we did yesterday on the homework where we found the p sub k plus 1 term, we want to figure out what that term is over here. So I would say we would have k plus 1 over 2 times, and if I do a little bit of work right here, 5 times k plus 1 minus 1, that's 5k plus 5 minus 1. So I would say times 5k plus 4. So I do the little bit of algebra. So this gives me clear direction as to like what I'm looking for in the end. That's how I'll know I've made my proof when I get to k plus 1 over 2 times 5k plus 4. And that'll be the signal that I'm done. Right below this statement is where you're going to do your algebra work. So after you make the statement, assume and show that, start by doing S sub k plus 1. So you go to S sub k plus 1. And S sub k plus 1 has to include all of the things for S sub k. 2 plus 7 plus 12 plus 17 plus 5k minus 1, or sorry, 5k minus 3. Plus an extra term. The k plus 1 term, the term that comes after the k. So we'll do 5 times k plus 1 minus And again, you can always break this up into the two things that they are. All of this stuff represents S sub k. This piece right over here, this is my k sub 1 term. Just my extra term that I would be adding to my sum. This, I got this by, so 5k minus 3 is my rule for the sequence. Okay, so like right up here, this is your rule for the sequence. So I have gone up to the k term, but I need the k plus 1 term, so I'm just subbing k plus 1 in for that k right there. And that's this right here. So it's 5 times k plus 1 minus 3. And then I'm going to do some algebra. Okay. We can say S sub k is really what? We assumed up here that S sub k was, in fact, k over 2 times 5k minus 1. All of those things we assume add up to that value. So we say equals k over 2 and 5k minus 1. So that's all of S sub k. This is still S sub k. And then over here I could do like my distribution and combining like terms. This would be 5k plus 5, which is, and then minus 3, which is 5k plus 2. So this is now representing a simplified a sub k plus 1. Now, I'd like to be able to add those things together. Trouble is, one of them has a denominator of 2. So it's like that very first term, that very first S sub k, that's a fraction. And in order to be able to add fractions, I need common denominators. So I'm going to have to do a little bit of work over here with my k sub 1 term. I'm going to have to multiply it by 2 over 2 so that I'll be able to add. Okay, so you're using your information from rational expressions. So this is k over 2 times 5k minus 1 plus 2 over 2 times 5k plus 2. And then both fractions have denominators of 2. So I'll keep my denominator of 2. And I'll just work with the stuff that's in the numerator. So k times 5k is 5k squared. K times negative 1 is minus k. And I'll add that with 2 times 5k, which is 10k, and 2 times 2, which is 4. I could combine some like terms, correct? So I have 5k squared plus 9k plus 4 over 2. And then remember, you're likely to get this trinomial, try to factor it. So we have 5k and k. And then think about factors of 4 are 1 and 4 or 2 and 2. Use your guess and check method to decide which numbers are correct and where they belong. Should use 4 and 1. so that I can do 5k times 1 is 5k, and 4 times k is 4k, and that'll add up to 9k. And I have 5k plus 4 over k plus 1, or sorry, 5k plus 4 times k plus 1 over 2. Look back at what you're trying to prove. Way up at the top. We want to show right here that k plus 1 over 2 times 5k plus 4. Is that the same thing? It's 5k plus 4 times k plus 1 over 2? Yeah. So you've proven it. You got the right formula. So you can say then, the statement is true. For all positive ends.